Module 10, Lesson 3. What we're going to do now is we are going to look at predicting the products of equations. One of the things that you need to be able to do is, if given the reactants in an equation, you need to be able to figure out what happens on the right-hand side, what is produced. So a couple of reminders here. The first thing, in order to predict the products, you have to be able to write the formulas correctly. This relies very heavily upon what we did in modules 6 through 8. So if necessary, you need to go back and review. I alluded to this in lesson 1, where I was talking with you about how, how we know where the subscripts come from and why you can't change them. The second thing that you're going to need to know is the kind of equation that you are dealing with. That's what we did in lesson 1 for this, whether it's a single replacement, a double replacement, a synthesis, a decomposition, or combustion. And you also have to remember Brinkelhoff. You have to remember the 7 diatomic elements because, well, that's quite necessary to getting this done correctly. So you have a practice sheet in your possession. I'm going to start off with some examples here that you can write on your own paper or just follow with me. This is done exactly like the practice sheet is. So what you're going to do is you are going to insert the reactants. What you need to do first is you need to start out by writing the formulas for the names that are given. So magnesium would just be written purely as Mg. Okay. Plus iodine. It is not I, because I is a part of Brinkelhoff. So we would need to write it as I2. Then we're left to figure out what happens over on the right-hand side. Well, I'm going to rely upon what I learned the other day with our different types of equations. And so if I look at this, I see 2 single elements. There's only one possible thing for them to do, and it's for this to be a synthesis reaction. One element plus another elm. This is still an element even though it's got the 2 on there. It's just iodine. So I'm going to have to put them together. Okay, what you do not do is you do not automatically keep the subscripts that are with the things. You don't go, oh, well, okay, there's 1 Mg and 2 I's, so let's just put that together. You're going to have to do some scratch work somewhere. You had 2 ways to go about this. You could do dots. Mg has 2 dots. I has 7. How do I know this? Well, this is back from module 6 when we learned how to do the valence electron structures. This is in group 2A. This is in group 7A. This has 2 dots. This has 7 valence electrons, so 7 dots. Magnesium, to get rid of its dots. Iodine can only accept 1, so it's going to take 2 iodines, and this other dot can go on top here. It's going to take 2 iodines to accept the 2 dots. Or some of you did charges. Magnesium would have a +2 charge, and I would have a -1. They have to add up to 0. That adds up to +2. I need 2 -1s to cancel out the +2. Either way you do it, I come up with the final answer of Mgi2. Now, in this particular case, Mg does have just 1 and I has 2 on both sides, but it doesn't always work that way, okay? So you need to do the scratch work to get it correct. So what I have is, this as final answer to predict. Now, what I'm not concerned about with this is balance. I'm simply asking you to write the skeleton equations. However, if you don't write the skeleton equations correctly, like you forget this 2, you'll never be able to balance it correctly. Okay, what about this one? Copper 2 chloride and sodium oxide. Well, we're writing formulas right off the bat here. If that's copper 2, that means it's Cu plus 2. Chlorine has a -1 charge. So the correct formula for copper 2 chloride is going to be CuCl2. Sodium plus 1. Oxygen's a -2. It'll take 2 sodiums to balance that out. Na2O. What I'm going to write down. So now, here is my left-hand side. What I figure out is going to come right. Well, let's look at what I have. I have a compound and I have another compound. When you have two compounds, add a double reaction. What we need to think of this as copper and the sodium need to switch places. If copper went with chlorine the first time, then that means now copper is going to go with oxygen. So if there's a plus 2 and oxygen's a minus 2, well, then they're going to cancel each other out. So on this side, it's just CuO. They cancel each other out because they both have a charge of 2. Now the Na is going to go with the Cl. Well, that's Na plus 1 and Cl minus 1. They cancel each other out as well. So it's just going to be NaCl. I realize entirely that numbers change. There's a 2 with this Na and there's not over here. There's a 2 with this Cl and there's not over here. The numbers do not have to go with their particular elements. The numbers are there because that's what it took to cancel them out and make them exchange electrons equally. So is it balanced? No. I would have to use coefficients in the front to balance it, but this is the correct skeleton equation. If you so choose, you can go so far as to balance it. If I put a 2 here, that'll make 2 NAs and 2 NAs, 2 CLs and 2 CLs. Now it's balanced if that makes you feel better, but you are not required to do that. Excuse me. Okay, here's another example. Sodium chlorate. Sodium is Na. When I see 8, what that means to me is that this is a polyatomic ion. Chlorate, if you look on your polyatomic ion list on your reference table, has a charge of -1, and it's ClO3. That means it'll take exactly one of each of those. So I have NaClO3. Well, looking at this, there's only one starting ingredient, which tells me that this has to be a decomposition reaction. Now, I don't think I have this available, so we're going to flip way back here through previous slides. We had this little table a long time ago in lesson 1, and it tells me exactly what to do. What we just had was NaClO3 right here. I see the things with ClO3. And what it says I should do is whatever metal I have, my M is the Na. The metal should go with chlorine, which means I'll have sodium and chlorine together. The correct formula would be this because Na is +1, Cl is -1, and then we're going to put plus O2. We're going to use this little chart to help me figure out exactly what happens. So, okay, so now we've got to get all the way back over here and see all the other work we've done. So we're going to do NaCl plus O2, okay? Because that's what it said to do, was to put the metal with chlorine and put O2 out there to the side. Is it balanced? No. I'm not concerned about that right now. I just want you to get the correct formulas, okay? All right, what about this one? We have aluminum plus hydrochloric acid. I have not required you at this point to know the acid names, so I'm giving you the formula for that. It's HCl, and in the block letters in the font that I'm using, that is an L, not an I. So how do we write aluminum? Well, just Al, and then I tell you right here that it's HL. Okay, so what next? Well, what is this? I see a single element and a compound, which tells me this is going to be a single replacement. And we're going to go all the way back again over here. I should have put these in. When I have a single replacement, I can, if that's hydrochloric acid, it says, we're doing this one. A metal replaces the H from acid. Now, one of the things, remember, that we had to do is when we had single replacement, we had some qualifications here, which was that the metal had to be reactive enough to do it. So the metal in the case that we're looking at was aluminum, which is right here, blue. Okay. If you look at these little arrows, what this arrow means is that from lithium down to copper, these things will react with oxygen to form an oxide. From lithium to lead, they will replace hydrogen from acid. Well, aluminum is in this little set right here that will replace hydrogen from acid, which means I can make this reaction happen. Remember, if it won't switch places, we put no reaction happens. But just to keep going with this, from lithium down to iron, these things will replace hydrogen from steam. And from lithium down to, I believe it's calcium, maybe sodium, will replace hydrogen from cold water. I'm not really sure where that ends. So I think it's calcium, hydrogen from cold water. So, oops. At least when you do this on the test, you'll have a piece of paper that you can hold up to it. I need a ruler. Okay, so since aluminum falls within the set that replace hydrogen from acid, what that means is we're good to go to do the rest of the equation. So that means aluminum and hydrogen will do a little switcheroo. That means hydrogen is going to come out by itself. Well, hydrogen is part of Brinkelhoff, so we're going to put H2. And then aluminum goes with chlorine. Well, if we do some scratch work down here, aluminum has a +3 charge. It's in group 3A on the periodic table. Chlorine has a -1 charge. In order to make the balance, we need 3 chlorines to cancel out the 1 aluminum. So the formula for this will be AlCl3. So that's what I'm going to write up here is AlCl3. So when they switch, our formulas change to make them satisfy the octet rule. And now we have a single replacement reaction. Now remember, if this wouldn't happen, then we just write no reaction if they won't switch places. Okay, here's one more. Dicarbon tetrahydride. Well, dicarbon means C2, tetrahydride means H4 plus oxygen. Well, how do we write the oxygen? Not like that because it's part of Brinkelhoff. I write O2. Now, when you look at this, a lot of people look at it and go, well, that's a single replacement reaction. I see a single element and I see a single element here in a compound. But this is our textbook recipe for combustion. I see a hydrocarbon, which is something with carbon and hydrogen, and then I see oxygen, which means if I look at the reference table, it'll tell me that the other things that come after this are always CO2 plus H2O. Like there's no debate about it. If I have this as a left-hand side, this has to be the right-hand side. Now, here's another one. Barium chloride. Well, you're going to have to do some scratch work for these. Barium chloride is going to be BaCl2. I'm doing the scratch work in my head to speed this up a little bit. Lithium phosphate will be LiPO4, and there'll be a 3 there, Li3PO4. What type of reaction is this going to be? Well, when I see a compound and a compound, this is going to be a double replacement. So what you can do is think of switching out metal for metal, like make these two things flip-flop. I need to put the Ba with the PO4. Well, Ba had a +2 charge, which is how that 2 got up here. P4 has a -3 charge. It will take 3 Ba's and 2 PO4s to cancel out. So the correct formula will be Ba3PO4 plus. Now put the lithium with the chlorine. Lithium's +1, chlorine's -1, so that will be LiCl. We now have the correct skeleton equation for barium chloride plus lithium phosphate. All right, what about this? Iron 3 and oxygen. Okay, well look, when I write this down, it's going to be the reason that this 3 is like a compound on the other side, you're going to have to know what charge it is. But just to write it, we're just going to put Fe. Oxygen will write as O2 because it's part of Brinkelhoff. What type of equation is this going to be? Well, if I just have 2 single elements right here, it has to be a synthesis. So our only choice is to put these 2 things together. Here's where I need the 3. That means it's a +3. Oxygen is a -2. So if you do the math of this, it'll take 2 Fe's and 3 O's to add up to 0 to trade electrons equally. So it'll be Fe plus O2 yields Fe2O3. Right, what about this one? Aluminum carbonate. Well, aluminum is 3. Carbonate. Remember, when it ends in ate or ite, ATE or ITE, it's a polyatomic ion. If you look it up on the polyatomic ion table, you'll see that it's a -2. So if I know that, my correct formula for this will be Al2CO3. Well, when I have only one reactant, the only thing that this could possibly be is a decomposition reaction. And even I have to go back to these and go, wait a minute, what does this make? I should have put this up here where we could see it easier. So when it's a carbonate, here's what's going to happen. We're going to get the metal with oxygen and then carbon dioxide, okay, because it's right here. So we're going to have a metal with oxygen, carbon dioxide, and then we're going to skip way back over here. I'm sorry for the delay with that. Oh, right there. So the metal is aluminum. So what that says is we're going to put aluminum with oxygen. Well, O is a -2. So it's going to be very similar. That'll be Al2O3 oxygen. No, there's no way. It had to be carbon dioxide plus CO2 in order to make the carbon still be in there. So we have Al2O3 plus CO2 because that's what it said to do. I had to put some thought into this, but the rest of it I just copied down. Okay, this one. I gave you the formulas this time because some of them I do like. I have the formulas. What is this going to be? Well, this is going to be a single replacement because I have a single element and a compound. The question is do they switch places? So we need to go backwards and we need to look and we need to see if they switch places. So we have calcium and sodium right here. Let's clear all this stuff off so we can see a little better. Okay, calcium is here. Sodium is down below it. So calcium is more active or more reactive. It is higher up than sodium. So what that means is that calcium will want to be in the compound. So when we go back to our example, okay, calcium is not in the compound, so it's going to kick sodium out, and calcium is going to go with the Cl. If you do the math of their numbers, that'll be CaCl2, and it's going to give sodium the boot and kick it out and say, nah, boot to the head, get over here, like out you go. All right, so it happens. And if it doesn't, we write no reaction. But it does happen in this case. Okay, what about this one? Sodium plus water. That's Na plus. Now it doesn't tell me if this is steam water or liquid water, if it's gaseous or what. This is also a single replacement. I see a single element and I see a compound. So if we go all the way back again, back here to this, we will see that sodium, it will replace hydrogen from steam, but it will not replace hydrogen from cold water. Remember earlier, like that appears to me to be a straight line right there. So if this was a gas, and the way that they could tell us is if it said a G on it, here's what would happen. The Na and the H would switch places. H2 would come out, and the Na would go with the O, Na2O. Okay? If this way, if it said H2 liquid, that G stands for gas and the L stands for liquid. If this was liquid, you would write no reaction because it is not supposed to take place if it will not replace the H from the cold water. Okay, so you would have to be given a little bit more info on some of them. If it was calcium, which goes either way, it doesn't matter. Like you would proceed to do the switching. So now it's your turn to practice. If you didn't make it all the way through this, that's okay. You know, like if you think you caught on, then get at it. If you need me for office hours, your job is to do these. I'm going to be, quite frankly, surprised if you don't have any questions for me, because in my face-to-face classes, this is usually a place where kids struggle. And it's usually because they don't write the formulas correctly, and therefore it messes them up with what they're doing. So please ask. if you're normal, then you're going to have questions. So if you can join office hours, and if not, let me know what office hours would work for you.